Hello, and welcome to Fall Asleep to Astronomy. I'm so happy you found this quiet moment with me tonight. Allow yourself to settle in wherever you are. Let the stillness of the night outside meet the stillness within your thoughts. Tonight, we aren't rushing anywhere. We're simply going to imagine on a cosmic scale, exploring a structure so vast it seems to belong only to the brightest of science fiction dreams. We're going to turn our gaze towards the star at the heart of our solar system and wonder what it might be like to truly capture all of its boundless, steady light. What if an entire civilization, far older and wiser than ours, decided to build a shell, a massive shell, around its own sun to harness every single ray of energy? It's an idea that touches on the limits of engineering and the boundless future of intelligent life. We'll drift through this possibility gently, considering not just the physics, but the poetry of such a colossal undertaking. If this quiet exploration of the universe brings you ease, a soft like and a quiet subscribe, help others find their way here too, so they can share this calm when you're ready. Let the grand scale of the cosmos make your own concerns feel wonderfully small. Imagine, just for a quiet moment, a civilization so patient, so clever, so impossibly old and steady-handed that it can shape matter into structures grand enough to cradle the light of an entire star. Not a thin ring, not a distant orbiting station, but an immense gathering of habitats and collectors drifting around a sun like petals drifting in slow motion around a windless bloom. You can picture it without effort, if you let your mind linger gently, a warm sphere of starlight kept close, its every ray caught and welcomed. Instead of wandering out into the cold, it feels almost like fantasy. Yet this idea did not come from a dreamer of stories. It came from a scientist, Freeman Dyson, a quiet thinker with eyes that seemed to look far into possibilities most of us would never think to name. He imagined a megastructure that could surround a star not as a single solid shell, but as a great loose swarm, a cloud of worlds and mirrors and machines, all drinking in the light of the sun they circled. The thought was simple in its bones. If a civilization ever grew so advanced that it needed more energy than its home world could offer, it would naturally reach for the nearest and brightest source, its own star. The light that rushes away from a star each second is unimaginably vast. In just one heartbeat's worth of time, our sun releases more energy than every invention, every fire, every generator humans have used since the first spark was struck. To imagine a species gathering every bit of that radiance is to picture an almost limitless reservoir of power. And yet, this idea is anchored in the plain logic of progress. As civilizations grow, their hunger for energy swells with them. Our own species has watched its needs rise century after century. We light up continents, power oceans of data, warm cities through bitter seasons, cool them through harsh summers. Every advancement brings more demand. But even so, all our efforts barely scratch the surface of what our sun casts aside effortlessly. Thinking of that contrast, our smallness beside a star's generosity brings a kind of soft wonder. It makes the thought of a star-sized power plant feel both impossible and strangely natural, like something a patient mind might eventually attempt after many thousands of years. If such a colossal undertaking were ever realized, the change in how we think about energy would be profound. Imagine no more fear of scarcity, no more slow depletion of resources, no more fragile dependence on the fragile crust of a planet. Instead, imagine a future built on the steady heartbeat of a star, always shining, always waiting, always giving enough for dreams we cannot yet imagine. But even with that picture in mind, the question lingers like a small, quiet whisper. What would a structure like that actually look like? And more curiously still, how could we possibly recognize one from so far away, perched on our tiny outpost of Earth, looking out through telescopes and algorithms? The trouble, as gentle and persistent as a distant hum, is that detecting such a thing from here would mean catching the faintest signs of deliberate engineering wrapped around another sun. When a civilization begins to tap the energy of its planet, the changes ripple outward slowly. When it begins to tap its star, the ripples become waves of light. To us, the discovery of such a civilization would feel both exhilarating and unsettling. Exhilarating, because the universe would suddenly feel less empty. Unsettling, because we would be looking at a species far older, far stronger, far more capable than we could yet comprehend. Recent studies have brought hints that stir imagination. Astronomers have noticed unusual patterns, strange infrared glows from 7 distant stars. Not bright flashes, not signals, just gentle excess warmth that should not, by natural laws, be there. These glows have sparked long debates. Could they be signs of engineered structures, swallowing starlight and releasing heat the way a blanket holds warmth? Or are they the breath of natural phenomena we have not yet learned to recognize? The universe often surprises us with its creativity, shaping dust into illusions and gas into mirages. But these particular stars carry a kind of quiet mystery, as though they insist on being wondered about. To appreciate why such glows matter, it helps to ease into an idea that has guided the way astronomers think about civilizations and their fires: the Kardashev scale. It was proposed in the year 1964 by a Soviet astrophysicist named Nikolai Kardashev, who suggested that the most meaningful way to measure a civilization's technological maturity was to look at the amount of energy it could command. He divided civilizations into 3 broad types, each more astonishing than the last. A Type 1 civilization is one that has full access to the energy of its home planet, not just sunlight and wind and water, but the restless strength hidden beneath the soil, the heat of the earth, the storms in the air, the steady tides. Imagine a species so capable it could channel the power of earthquakes gentled and tamed into the lamps of its cities, or borrow the force of volcanoes without fear. Humanity is not there yet. We are still learning, still reaching. A Type 2 civilization stretches even further. It does not stop at the energy of a single world. Instead, it gathers the shine of its entire star. This is where Dyson's idea becomes relevant. Such a civilization, wrapped around its star with structures basking in radiance, would have access to almost everything that star could offer. And beyond that is a Type 3 civilization, whose reach is so enormous it could gather the energy of an entire galaxy, billions of sunlit furnaces humming in harmony under its guidance. Imagining such a species makes the mind feel small in the gentlest possible way. The beauty of the Kardashev scale lies in its simplicity. As a civilization grows, so do its needs, and those needs inevitably push it toward bigger, bolder ways of catching the light that sustains it. That is why the idea of a Dyson Sphere fits so naturally. It is not a fanciful structure built for spectacle. It is an answer to an ever-expanding hunger. But understanding the idea is only the first step. The deeper question, soft and persistent, is how we might find such a thing. The key lies in a subtle kind of light, not the visible light that stars scatter, but the warm, gentle glow we call infrared radiation. Our eyes cannot see it, but our instruments can, and this ability has opened a whole new window into the universe, letting astronomers detect warmth the way one might sense a hand held near a fire even with eyes closed. Infrared astronomy lets us study the universe through this invisible glow. Every star, every planet, every swirling cloud of dust emits heat, and that heat becomes a story told in wavelengths longer than the ones our eyes know. When scientists look in infrared, they see things that would be invisible through traditional telescopes. They can sense cool objects, hidden structures, or warmth that suggests something unusual is happening. This field began in the quiet middle of the 20th century, when astronomers experimented with early infrared detectors. Their instruments were crude compared to today's delicate observatories, but they paved the way for what would come. Little by little, the universe revealed textures no one had imagined. Soft halos of heat around aging stars, faint whispers of light from distant galaxies. Decades later, these early efforts blossomed into a fleet of advanced observatories, including the Wide Field Infrared Survey Explorer, often called WISE, and the James Webb Space Telescope. WISE gently swept across the sky, mapping it in long, warm wavelengths and uncovering countless hidden objects. The James Webb Telescope looks even deeper, with mirrors shaped like petals of a golden bloom, sensing the faintest warmth from stars that have shone for billions of years. Infrared astronomy matters because a Dyson Sphere, if it existed, would not shine brightly in visible light. Instead, it would swallow much of its star's radiance and re-emit it as heat. To us, that would appear as an unexpected excess of infrared glow, a warmth out of place. Dyson himself suggested this: if such a structure were ever built, it would be visible, not by its shape, but by its warmth. This was more than a thought experiment. It was a roadmap, a gentle hint that if we searched for this kind of heat, we might one day notice something crafted by intelligence far from Earth. And indeed, this line of thinking guided astronomers to those 7 mysterious stars whose warm signatures do not quite match ordinary expectations. Maybe they are nothing more than strange clouds of dust. Maybe they belong to categories of stars not yet fully understood. Or maybe, in some quiet corner of the universe, an ancient civilization has begun gathering the light of its sun. We cannot claim to know, but the wondering itself feels like an invitation to look closer. Modern infrared telescopes expand that invitation by sensing faint thermal emissions from stars, planets, and galaxies. They give us a new language for reading the universe. WISE, launched in the year 2009, mapped the entire sky in infrared light. Its observations revealed stars shrouded in dust, galaxies glowing softly, and countless asteroids drifting through our own solar neighborhood. Its maps form a foundation, a quiet library of warmth that astronomers continue to explore, searching for anomalies that whisper of something extraordinary. The quiet patience of instruments like the Wide Field Infrared Survey Explorer becomes even more meaningful when we remember what it is truly searching for. Its gift lies not only in mapping the sky, but in noticing when a star glows just a little warmer than it should. That faint, unexpected warmth is the essence of the search for Dyson spheres. When WISE measures the long, gentle wavelengths of heat drifting through space, it gives scientists the chance to notice an imbalance, a softness in the glow that natural processes alone may not explain. These small anomalies, tucked between ordinary starlight and the hush of cosmic dust, might one day be the whispers of advanced engineering. Among the many efforts to explore these possibilities, there is an especially thoughtful project led by a group at Uppsala University. They call their initiative AESTI, a name that feels almost like a small breath, fitting for a team searching for subtle warmth in the dark. Their work begins by watching the sky through the combined memories of several space observatories. They gather precise measurements of star positions and distances from the Gaia mission, near-infrared observations from a project known as 2MASS, and mid-infrared readings from WISE itself. Each of these data sets carries its own quiet texture, its own shade of light, its own small imperfections. Bringing them together forms something like a portrait, a star painted not only in brightness, but in warmth, distance, motion, and age. To make sense of this immense collection of information, they rely on machine learning systems tuned to notice the subtlest irregularities. If you imagine someone patiently sifting through millions of grains of sand, searching for just 7 or 8 that shine differently under moonlight, you will have some sense of what these algorithms do. Convolutional neural networks, carefully trained and guided, move through the data with an attentiveness impossible for human eyes alone. They remove false positives, smooth out noise, and bring forward the stars whose warmth does not behave as nature predicts. It is a kind of digital intuition, built slowly through practice, that begins to sense what deserves a closer look. Once these promising stars are gathered, the team turns to modeling. They imagine many possible shapes and temperatures a Dyson structure might have, building theoretical models the way someone might sketch countless silhouettes against a candle's glow. With each model, they calculate what kind of infrared light such a structure would emit. Then, they compare those imagined glows to the actual measurements from the sky, checking for a quiet match. It is not a single comparison, but thousands, perhaps millions, each one a small step toward understanding whether a star's warmth is ordinary or out of place. Through this slow, careful process, the team has identified 7 stars that carry an excess of infrared light that nature does not easily explain. All 7 belong to a class known as M dwarfs, small, dim stars whose light is gentle, like coal left to smolder. Because these stars are so faint, any extra warmth stands out more clearly. Seeing unusual heat around them is like noticing a candle burning slightly brighter inside a closed room. It may be nothing more than a natural quirk, but it is unusual enough to make people wonder. These discoveries are meaningful not because they prove anything, but because they show what can be done with quiet persistence and old data. Much of the light used in this search was gathered years ago, long before the idea of this project even existed. It reminds us that the universe hides possibilities even in things we think we understand. A dusty record from WISE, a faint measurement from 2MASS, a precise distance from Gaia, all can become pieces of a mystery if examined with new curiosity. The search for Dyson spheres and for all forms of technological signatures moves forward thanks to constant improvements in infrared astronomy. This field has grown steadily more precise, letting us notice details too soft, too faint, or too tangled with noise for older instruments. One of the most transformative advances is the development of adaptive optics. Earth's atmosphere, as gentle as it looks from below, bends and blurs starlight as it travels through layers of shifting air. Adaptive optics corrects for this distortion in real time, smoothing out the ripples like a steady hand calming the surface of a trembling pool. With this clarity, astronomers can isolate faint threads of infrared glow, distinguishing them from the haze that surrounds all distant objects. At the same time, machine learning has become an indispensable part of the search. These algorithms can wade through oceans of data, teaching themselves to recognize the delicate fingerprints of stars behaving strangely. They notice patterns far thinner than a human mind could track, subtle hints that something is mismatched, something is unexpectedly warm, something might deserve another look. When millions of stars must be checked, and only a handful might whisper of something extraordinary, such tools are not luxuries, they are necessities. And then, there is the James Webb Space Telescope, a giant mirror of gold petals unfolding in the quiet beyond Earth. Its power lies not only in its size, though its primary mirror is more than 16 times larger than that of WISE. It lies in its sensitivity to the very wavelengths where Dyson spheres would glow. If such structures exist, they would radiate most strongly in the mid-infrared range, where warmth escapes like soft breath. The James Webb Telescope was built to see in that range with exquisite precision, catching thermal signals so faint they might as well be whispers from across the universe. But even this powerful instrument has limits. Its schedule is packed months, even years, in advance, filled with pressing tasks, studying distant galaxies, tracing the birthplaces of stars, examining the atmospheres of exoplanets. The telescope cannot spend large blocks of time scanning for Dyson spheres alone. Yet, when its gaze does fall upon a star with an unusual glow, the results can be transformative. A single observation might strengthen a suspicion or gently dissolve it into dust. Infrared light is not the only messenger that might reveal artificial structures. Radio astronomy, too, plays a role in this quiet search. The Very Large Array in New Mexico, with its long, delicate arms arranged across the desert like a patient mechanical flower, listens for radio waves from every corner of the sky. Radio signals carry their own stories: the murmurs of gas clouds, the storms of distant planets, the hum of galaxies. If a Dyson sphere were collecting and transforming stellar energy, it might release certain kinds of radio patterns as a byproduct. The Very Large Array can detect these soft emissions, offering a complementary angle to infrared observations. When both kinds of light are studied together, the picture becomes fuller, gentler, more complete. The discoveries from Uppsala University are not the only hints stirring curiosity. Another study, titled "A Data-Driven Search for Mid-Infrared Excesses Among 5 Million Main Sequence FGK Stars," conducted by Gabriela Canardo and David W. Hogg, uncovered 503 stars that shine more warmly in the mid-infrared than expected. Their approach echoed the careful methods of the AESTI project. They used data from Gaia, 2MASS, and WISE to predict what the infrared brightness of each star should be. When a star glowed significantly brighter than the prediction, it was marked as unusual. From nearly 5 million stars, the list was slowly trimmed down. Additional filters removed: false positive stars with measurement errors, stars with dust misclassified, stars whose glow could be explained by simpler things. In time, the vast sample was narrowed to 53 objects, 53 warm, lingering anomalies among millions. Some of these stars show signs that could easily be mistaken for technological signatures. For instance, one star displays warmth that could resemble an extreme debris disk, a vast swirl of dust and broken material circling a star, like snow drifting endlessly in a windless valley. Such debris can trap starlight and re-radiate it as heat, creating an infrared glow that mimics the warmth a Dyson structure might produce. Yet, this particular star is also older than expected for such a dramatic disk, raising questions about whether our models of planetary evolution may need revision. Perhaps the disk has survived longer than thought. Perhaps another process is at play, or perhaps there is something stranger, something we have not yet named. The implications of these findings are both delicate and profound. If any of these anomalies turn out to be true Dyson spheres or even partial Dyson swarms, it would be undeniable evidence of extraterrestrial intelligence, not in metaphor, not in theory, but in the quiet certainty of measured light. It would mean that somewhere out there, another species looked at its star and thought, "We can use this light more fully." But science must remain calm. Dust clouds, debris disks, and unusual natural processes can mimic these signatures with surprising ease. The universe is a master of illusion, shaping heat and shadow into patterns that tempt our imaginations. For every promising candidate, follow-up observations are essential. Only by studying each star more closely, checking its age, its environment, its spectrum, its motion, can we begin to understand whether its warmth is a natural quirk or something crafted by hands we will never meet. The quiet uncertainty surrounding these unusual stars has become part of the story itself. Each time scientists notice an excess glow in the long, warm wavelengths of infrared light, a gentle controversy rises around it, as soft and persistent as mist. The difficulty lies in telling whether this warmth comes from something natural or from something shaped by deliberate hands. Infrared excess, by itself, is like a murmur, meaningful only when contrasted with everything else a star should be doing. And with each faint signature comes the same challenge. The vast distances between us and these stars stretch every signal thin, making interpretation a fragile art. Many of the stars under study live thousands of light years away, tucked in regions where their glow must journey for millennia across empty space before reaching us. During that long passage, even the strongest light fades into something delicate, something easy to misunderstand. The farther the source, the fainter the whisper, and the harder it becomes to gather firm, trustworthy measurements. A single misunderstanding, a subtle distortion in the data, can make a star appear warmer or stranger than it truly is. Some researchers suggest that our knowledge of how stars and planets behave is still incomplete, and that these anomalies may be pointing toward new astrophysical processes rather than technological constructs. In this quiet tug-of-war between possibility and caution, the truth remains patient. Humanity has wrestled with the question of life beyond Earth for centuries. Long before telescopes and detectors and algorithms, the question lived as a longing, a philosophy, a story told around fires. Over time, that longing transformed into a scientific search, structured, careful, and humble in its methods. Today, scientists look for life by seeking two kinds of signs: technosignatures and biosignatures. Technosignatures are traces of deliberate activity, excess energy, unnatural emissions, engineered structures, signals shaped by intention. Biosignatures, in contrast, are the quiet fingerprints of biology-specific gases like oxygen or methane floating in a planet's atmosphere, or patterns on a surface that hint at chemical cycles stirred by living things. Modern observatories make this search gentler and more precise. The James Webb Space Telescope, with its wide golden mirror unfolding like a careful blossom, can read faint heat signatures from distant exoplanets. In the soft stretch of infrared light, it can sense atmospheres, looking for gases that might reveal the presence of life. Dozens of worlds have already been placed into the possibly habitable column, their temperatures mild enough, their orbits steady enough, their atmospheres intriguing enough to earn a closer look. Working alongside Webb is the Transiting Exoplanets Survey satellite, watching for tiny dips in starlight as planets pass in front of their suns. Each dimming is a quiet gesture, a small wave from a distant world. TESS has found thousands of such candidates, many waiting patiently for Webb or other telescopes to reveal their secrets. Together they form an intricate dance, one telescope detecting the faint footprint of a world, another leaning in to study its breadth. The coming decades promise even clearer eyes on the sky. Proposals like Louvoire and Habex dream of telescopes able to image planets directly, capturing their reflected light with clarity unimaginable today. These future instruments would not simply infer the presence of atmospheres. They would examine them in exquisite detail, seeking hints of life or technology in their spectral fingerprints. Ground-based observatories will join this effort as well. The extremely large telescope, with its enormous mirror, composed of many interlocking segments, will gather starlight with unparalleled power. It will be able to glimpse exoplanet atmospheres, separating tiny strands of color that reveal their chemical makeup. And the square-kilometer array, a vast expanse of listening dishes stretching across the land, will search not for light but for radio waves, signals that might hint at distant technologies or unusual cosmic processes. Between these instruments, the universe will have fewer places to hide its secrets. But the search for life does not look only outward. It also turns closer to home, to the icy moons of our own solar system. Europa, with its cracked shell of ice, and Enceladus, with its shimmering plumes. Both harbor subsurface oceans dark and deep. These hidden seas, warmed by internal tides and chemical reactions, may cradle microbial life. Missions like Europa Clipper, along with potential future explorers sent to Enceladus, aim to taste the waters rising from these worlds, searching for the faint signatures of living chemistry. Even if the life they find is simple, just a few persistent microbes, it would rewrite our understanding of how common life might be across the cosmos. Every step in these searches, whether they lead to confirmation or to disappointment, nudges us closer to understanding our place in this vast, silent expanse. The journey pushes the limits of our technology, challenges our assumptions, and stirs our shared imagination. Each innovation, each refined instrument, each improved method acts as a small lantern carried into the unknown, illuminating possibilities once hidden. And behind all this effort is a question so simple and so heavy that it has followed humanity across ages. Are we alone? Most of us have watched science fiction with a quiet wonder, imagining what alien life might look like. Some envision beings not so different from us, carbon-based organisms with familiar structures and familiar needs. Others imagine shapes far stranger, forms that do not resemble anything on Earth. One famous writer, Isaac Asimov, described alien life as living stone, beings whose chemistry was built not from carbon, but from silicon. This idea once felt like a delightful impossibility, something belonging firmly to the realm of fiction. And yet, the thought has lingered. As we look further into the universe, and deeper into our own chemistry, the question becomes harder to dismiss outright. Could silicon-based life truly exist? Could there be worlds where the foundations of biology are shaped from different building blocks, responding to different environments, guided by different laws? To begin answering that, we must start with what we know. Carbon is the backbone of life on Earth. Without it, none of the structures that hold us together could exist. About 18% of the human body, roughly 26 pounds in an average adult, consists of carbon. It forms a lattice for proteins, fats, carbohydrates, sugars, and countless other organic molecules. It shapes the double helix of DNA, cradles the instructions for life, and binds together the substances that let us move, breathe, think, and dream. Carbon does not serve only us. It threads through the lives of plants as well. Every breath we exhale carries carbon dioxide, a gas essential for photosynthesis. In the presence of sunlight, plants take this carbon dioxide and weave it into oxygen and glucose fuel for themselves and, through an intricate chain of exchanges, for us. Carbon dioxide also acts as a quiet guardian of warmth, capturing heat in Earth's atmosphere and helping maintain the temperatures that allow life to flourish. Without this delicate balance, our world would be cold, barren, and uninhabitable. These roles highlight why carbon has become the foundation of biology here. Yet the universe is vast, with environments far different from our own, and within that vastness, the possibility, however faint, that life might arise from a different element lingers like a question just beyond reach. If the greenhouse effect on Earth were not as generous as it is, even with all the complications it brings, our world would be a frozen sphere drifting through space. The warmth we know, the climates we navigate, the softness of nights, and the gentle rise of mornings all exist because certain gases, including carbon dioxide, hold heat close enough for life to flourish. Without this delicate containment, oceans would turn to ice, winds would whisper without moisture, and the landscapes we recognize would fade into stillness. It is strange to think that the same gas capable of unsettling our climate today is also a quiet guardian that once kept our planet from slipping into eternal winter. But carbon's importance stretches far beyond the breadth of the atmosphere. It weaves itself into our everyday world, so fully and so quietly that we barely notice its presence. Almost everything familiar to us, from the fabric resting against our skin to the medicines that steady our health, from the warm ceramic cup we lift in the morning to the walls that shelter us, from wooden instruments making soft music to the phones and laptops glowing in our hands, contains carbon as part of its hidden architecture. It supports books, plastic, fuel, and food. It shapes the world we build and the bodies we live inside. We are surrounded by it in ways so intimate they become invisible. Carbon is not the only ingredient in these things, nor in the intricate machinery of living organisms, but its versatility makes it irreplaceable. Among all the elements scattered across the periodic table, few have the patience and balance carbon possesses. Adaptable, but not reckless. Reactive enough to build links, but not so reactive that everything collapses into sparks. According to astrobiologist Robert Hazen, any element that hopes to serve as a foundation for life must be able to form bonds with other atoms without burning itself away in the process. It must be strong enough to hold information, flexible enough to create complexity, and stable enough to last through the long, slow journey of evolution. Carbon fulfills these tasks with an elegance unmatched by any other known element. It is the quiet, master builder of Earth's biology. Yet the question rises softly. Is carbon truly the only foundation life could ever use? Or is it simply the foundation we became accustomed to because this is the world we grew up in? If we step back from the familiarity of our planet and imagine the universe without carbon, imagine distant places where its presence is thin or absent, what element might take its role? The answer, or at least a possibility, lies directly beneath carbon in the periodic table: silicon. Silicon is one of the most abundant elements on Earth, making up roughly 28% of the planet's crust. It hides in sand and stone, in amethyst that glows violet in sunlight, in clay, granite, quartz, and countless minerals. It is part of the glass in windows, part of the dust on windy plains, part of the sparkling grains that slip through our fingers on a quiet beach. And just as carbon finds use in everyday life, silicon rests in the heart of much of our modern technology. Computer processors, the tiny minds of our devices, rely on silicon for their intricate pathways. The element also appears in cosmetics. soft gels, wound dressings, contact lenses, sealants, paints, and high-performance materials used in aircraft and construction. Its presence is vast, and its uses are many. But what of its role in life itself? According to researcher Milton Wainwright, silicon may have played a part in the earliest whispers of biology on Earth. His studies suggest that silicon dust arriving from space may have stimulated bacterial growth even in environments lacking nutrients. Billions of years ago, during the turbulent youth of our solar system, comets containing silicon-rich materials may have struck the young Earth, delivering grains that encouraged the emergence of simple life. If this is true, then silicon was not simply a bystander in Earth's history, but a quiet assistant, nudging early chemistry toward biology. Even now, silicon influences life in subtle ways. In plants, it strengthens stems, protects against pests, shields leaves from toxins, and reduces water loss. It acts almost like a thin, invisible armor, improving resilience. In humans and other animals, silicon contributes to bone health, wound healing, and connective tissues. Some research suggests it may help lower the risk of cardiovascular disease and even play a role in reducing certain neurological risks. It is not the foundation of life, but it is a gentle helper, shaping health and growth in ways we rarely notice. So why, then, does silicon often appear in discussions about alien life? The first reason lies in its chemical kinship with carbon. Elements sit on the periodic table not by accident, but by pattern. Silicon rests directly beneath carbon because the two share similar outer electron configurations. Both elements are tetravalent, meaning they can form 4 bonds, like hands reaching in 4 directions. This capability is essential for building complex molecules. It allows, at least in theory, for long chains and intricate structures similar to those formed by carbon. If life requires an element able to form frameworks, bridges, and long networks of atoms, silicon seems a logical candidate. The second reason is grounded in experiment. In the year 2016, a team at the California Institute of Technology, led by Francis Arnold, managed to coax living E. coli bacteria into producing proteins that incorporated silicon-carbon bonds. This achievement demonstrated that silicon can be woven into biological structures by living systems, something once thought impossible. The study showed that under guided conditions, biology could expand its chemistry to include silicon in meaningful ways. While this does not prove silicon-based life exists, it proves it is not forbidden. To even approach the question of whether silicon could replace carbon, we must revisit the meaning of life through the eyes of biologists. Researcher Norman Pace describes life as a system capable of self-replication and adaptation, an organism that can copy itself and improve enough to overcome the challenges posed by its environment. For a chemical system to support such a journey, its building blocks must adapt quickly, respond to pressure, engage in evolution, and maintain stability through time. Carbon-based molecules are excellent at this. They respond to heat, pressure, and water with a balance that supports growth. But life also requires ecological conditions beyond chemistry. It thrives in environments with oxygen, nitrogen, moderate temperatures, and water, a solvent so effective that it dissolves and transports countless molecules, letting them collide and merge and separate again. In water, compounds that were once isolated can meet and form new structures. Carbon fits easily into this dance. It forms strong, stable frameworks for cells that float, divide, and breathe in water-based environments. Here lies the challenge for silicon. In water, silicon tends to form structures that are rigid and brittle, breaking before they can adapt. Silicon bonds dissolve poorly, react heavily, and resist the fluidity needed for life as we know it. In simple terms, silicon struggles to create the flexible, intricate molecular networks that carbon forms with ease. So the short answer is, silicon-based life, at least in water, seems unlikely. But that is not the end of the story. Because life may not require water, if the universe contains worlds ruled by liquids other than water liquids, where silicon behaves differently, then silicon-based biology becomes more than a thought experiment. Scientists have proposed that liquid ammonia, common on worlds like Jupiter and Pluto, could act as an alternative solvent. Ammonia has properties that might allow silicon to engage in more dynamic chemistry. But ammonia is also highly toxic to structures familiar to us, and its pathways are still poorly understood. Without experimental evidence, the idea remains hypothetical. Scientists have yet to fully test how silicon behaves in such environments, or whether molecular complexity can rise from ammonia's cold, reactive depths. For now, the question lingers in a soft space between certainty and curiosity. Carbon remains the unrivaled architect of life on Earth. Silicon remains a versatile companion, a helper, a widespread and resilient element that shapes much of our world, but not the heart of our biology. And yet, in the quiet vastness of the cosmos, where temperatures range from burning to frozen, where pressures can crush or stretch, where solvents other than water may flow in alien seas, there may still be rooms for possibilities we have not yet seen. Beyond the thought of liquid ammonia, there are other strange and unsettling solvents scattered through the universe, liquids that feel almost hostile to the life we know, yet might cradle a different kind of chemistry. One of the most striking among them is sulfuric acid, a substance so fierce that it can dissolve metals without leaving the faintest trace behind. It is the kind of liquid that seems born to erase, not to sustain. And yet, in that corrosive quiet, silicon behaves differently. Odd as it may seem, silicon can form structures within sulfuric acid, adapting itself to a solvent that carbon-based life would find instantly fatal. This possibility opens a small, trembling door in a world soaked with sulfuric acid like the cloudy shroud above Venus. Silicon-based organisms might, in theory, take shape. Sulfuric acid is not the only environment where silicon could explore its potential. In the cold, outer reaches of our solar system, solvents like methane and ethane become liquid under low temperatures. On Titan, one of Saturn's moons, these liquids gather into lakes and seas, sloshing gently under a thick atmosphere. Methane rain falls from orange clouds, rivers carved from ethane wind across icy plains. In places like Titan, silicon compounds could form and drift through those strange seas, but cold slows down everything. Reactions, movements, dissolving, bonding. Even if silicon could, in theory, combine with other elements in that frigid darkness, the pace would be so sluggish, so hesitant, that the spark of life might never ignite. Chemistry thrives on motion, on collisions, on persistence, and the deep cold of Titan smothers those chances beneath its frozen breath. Silicon's structural potential remains a tempting thought, though. Like carbon, it can reach out and bond with many of the elements essential to life as we understand it: nitrogen, hydrogen, oxygen, phosphorus, sulfur, and even a variety of metals. It can, at least on paper, form the scaffolding needed for something alive to take shape. But when we look closer, its limitations begin to unfold. Silicon resists bonding at temperatures that feel comfortable to us. At anything between roughly 32 degrees Fahrenheit and 212 degrees Fahrenheit, silicon becomes unwilling, uncooperative. It will not form the complex patterns that carbon creates with ease. Only at extreme temperatures, very high or very low, does silicon wake up chemically, which makes building intricate frameworks much more difficult for any other element that would want to join it. Then there is the matter of silicon bonding with itself. Carbon links to carbon with astonishing strength and flexibility. Its chains can stretch long, curl, bend, twist, and fold into the three-dimensional shapes needed for proteins, carbohydrates, and the delicate spirals of DNA. Carbon-to-carbon bonds are the quiet stitches that bind life together. In contrast, silicon-to-silicon bonds are fragile things. They break easily and cannot support the vast frameworks required for living cells. To understand this difference, think of a diamond, a crystal, formed entirely from carbon. It is a testament to the strength and stability of carbon bonds. Silicon could never build such a structure. That gap in ability hints at how deeply life relies on carbon's unique talents. Silicon does, however, form strong bonds with oxygen. In fact, it prefers oxygen so intensely that on Earth, silicon is almost always found as silicon dioxide, a compound that takes the form of sand. It is everywhere, silent and steady, but stubbornly unwilling to separate. For life to use silicon the way Earth life uses carbon, silicon would need to be far more accessible than this. Instead of offering itself up in flexible chains, silicon clings to oxygen in rigid lattices, which makes the element far less adaptable. If humans were somehow reimagined as silicon-based creatures, exhaling the byproduct of our metabolism would mean breathing out grains of sand instead of carbon dioxide, a quiet, strange image that reveals how differently such a body would function. Carbon's role becomes even clearer when we think about food. Everything we eat is a story of energy folded into molecules. When we feel tired, a good meal restores us. But the source of that relief is not the food itself, it is the carbon-based compounds hidden within it. Glucose, one of the simplest and most essential sugars, is built entirely on a carbon backbone. When food is scarce, another carbon compound stored in our liver, starch, steps in, breaking apart slowly to release glucose when needed. These processes depend on carbon's ability to form stable, responsive bonds. If carbon were replaced with silicon in these structures, the molecules would crumble under their own instability. They would not bend or store energy properly. They would not respond to changes in the environment. The delicate loops of metabolism would collapse, leaving no foundation for the rhythms of life. Even if silicon could never replace carbon fully, it is still possible that silicon-based life could evolve in environments far different from Earth. But it is highly unlikely that such life would exclude carbon entirely. More probable is a blended chemistry, a creature whose structure relies partly on silicon but still leans on carbon for complexity. Here on Earth, no organism is purely silicon-based, yet silicon plays a surprisingly gentle supporting role. Plants draw silicon into their tissues to strengthen themselves, forming subtle reinforcements against wind, pests, and disease. Animals use silicon to support bone health and to help in healing wounds. In humans, trace amounts of silicon flow quietly through our systems, influencing connective tissue and resilience. It may not be the heart of our biology, but it is woven into our lives more than we often realize. Our oceans offer one of the clearest examples of silicon's presence in biology. Diatoms, tiny algae that drift through sunlit waters, surround themselves with shells made entirely of transparent silicon dioxide. These shells look like miniature glass sculptures, each one unique, delicate, and intricately patterned. They are not silicon-based life forms in the pure sense, but they prove that silicon can indeed become part of a living organism's architecture. They are like small reminders from nature that silicon has its place in the story of life, even if not at the center. But what of life elsewhere beyond Earth, beyond the comfort of water and warmth? According to a study led by Ricardo Gabato, the ideal environment for silicon-based organisms would be strikingly different from our own. Such life would require worlds with almost no oxygen or water, temperatures above 428 degrees Fahrenheit or below 32 degrees Fahrenheit, and atmospheric pressures far higher than anything on Earth. The solvent bathing such life would likely need to be sulfuric acid or methane liquids that seem, from our perspective, almost hostile to the idea of life. Some worlds in our solar system echo these strange requirements. Titan, the largest moon of Saturn, holds lakes and seas of methane and ethane. Its atmosphere is thick with nitrogen. Its temperatures are low enough to slow nearly all chemistry. Yet the ingredients for silicon-based reactions could linger in its dim orange haze. Venus, in contrast, sits under crushing pressure, drenched in heat and wrapped in swirling clouds of sulfuric acid, while its surface glows with temperatures that would destroy most known materials. Its upper atmosphere contains layers where the conditions resemble the requirements suggested by researchers. Within those yellow clouds, silicon-containing molecules might theoretically form, though even there, carbon would likely dominate due to the high carbon content in Venus's atmosphere. Surprisingly, another candidate for silicon-based life emerges from the realm of theory: carbon planets. Only one confirmed carbon planet is known so far, an exoplanet called 55 Cancri E, located about 40 light-years away. These planets form farther from their parent stars, in regions where carbon becomes abundant and mixes with extreme pressures. Their surfaces may hold oceans of heavy hydrocarbons like butane. In such an environment, silicon might bond with carbon more readily. Yet those silicon-carbon bonds, known as silicon carbide, are remarkably strong. Their durability means that breaking them apart, an essential part of life's chemical cycling, would require enormous amounts of time and energy. And so, even in an environment seemingly suited for silicon-based organisms, the stubborn strength of these bonds becomes a barrier, limiting how gracefully such chemistry could evolve into something alive. Even if life were to begin on a carbon planet, such a journey would unfold with an almost unimaginable slowness. Chemistry would take its time, weaving delicate threads under conditions far harsher or more unusual than anything familiar to us. Silicon-based life, if it ever stirred somewhere among the starlit spaces, would likely endure an even more prolonged beginning. And if just for a quiet moment we allow ourselves to imagine that silicon organisms have existed long enough to leave their trace somewhere, we are faced with a question both simple and impossibly complex. How would we ever know? Science fiction has offered us its own answers: creatures that resemble living stones, crystalline beings rising from molten caverns, beings sculpted from minerals instead of flesh. In stories like Star Trek, life built from silicon emerges from the deep rocks of alien worlds, slow and powerful, ancient and inscrutable. These images linger in culture, shaped by imagination more than evidence. The truth, however, is far less certain. If silicon-based life exists, it may not resemble stone at all. We humans are made from carbon, yet our bodies are soft and warm, flexible and fragile. Diatoms carry silicon in their glass-like shells, yet they look nothing like solid crystals. Form does not reveal chemistry. Materials do not dictate appearance. Scientists admit, with a humility shaped by the vastness of the unknown, that we have no idea what silicon life might look like. It could be smooth or jagged, hard or fluid, tiny or sprawling. It may not resemble an organism in any sense we understand. It might not even have the complexity to think, adapt, or sense the world. Some researchers quietly suggest that silicon life, if it exists, would probably not achieve intelligence or intricate biological structures. It might remain simple, slow, barely noticeable. We would not know where to look, what molecules to detect, or what clues to follow. Without technology or unmistakable patterns, such life could go unnoticed, blending seamlessly into the minerals of its world. We could scan an entire landscape and fail to realize that part of it was alive. This difficulty reveals something profound about ourselves. We struggle to imagine life thriving under conditions different from those we know. Every example of life we have ever encountered lives within the boundaries of Earth, breathing, drinking, growing within familiar pressures and temperatures. Because of this, our space missions reflect our expectations. We search for organisms that look like us in the ways that matter chemically: carbon-based, water-dependent, shaped by moderate temperatures and stable atmospheres. Our tools are designed to detect compounds and patterns we understand. Even our questions are shaped by the only biology we've ever seen. For now, it is impossible to confirm whether silicon life exists anywhere. Our science is not yet mature enough. Our detectors cannot yet find what we have not learned to conceptualize. But the cosmos is vast, too vast to make confident declarations. With billions of galaxies and uncountable planets, it is difficult to imagine that all alien life would mirror Earth's chemistry. The diversity of the universe suggests possibilities beyond our intuition. Somewhere, perhaps, life takes forms that Earth biology cannot predict. Since the first telescopes reached toward the sky, humanity has been transfixed by the idea that life might exist beyond our world. We sent rovers to Mars, letting their mechanical footsteps press into rusty dust in search of ancient microbes. We launched probes to Venus, allowing them to descend through layers of suffocating heat and acidic clouds, listening to them for a few brief minutes before the planet's fierce conditions swallowed them whole. We studied Jupiter's icy moons, imagining the sloshing oceans beneath Europa's frozen shell. And through all these efforts, a single quiet assumption guided our choices. Life, wherever it might be, would resemble Earth's biology. This belief gave us the Goldilocks zone, a small ring around a star where temperatures are warm enough for liquid water but cool enough to prevent boiling. It is neither too hot nor too cold, a gentle belt where life as we know it might thrive. For decades, this zone defined the heart of our search. We pointed telescopes toward planets that drifted in this warm interval. We looked for atmospheres that echoed our own. We hoped to find oceans or lakes, clouds or rivers. We measured hints of methane or oxygen, searching for patterns familiar to us. In many ways, our search for extraterrestrial life has been a search for a second Earth. But what if this Earth-centered perspective has quietly narrowed our vision? What if our longing for resemblance has blinded us to life that thrives under entirely different rules? The thought is humbling and disorienting. If life can exist without water, then the Goldilocks zone becomes only one possibility among countless others. Whole worlds could flourish in regions we have long ignored, beneath conditions we once considered hostile. This thought invites us toward a molecule often overlooked: ammonia. At first glance, ammonia feels too mundane, too harsh, too associated with cleaning fluids and caution labels to symbolize life. Yet chemistry rarely conforms to expectation. Ammonia can stay liquid at temperatures so cold that water becomes rigid stone. It can dissolve many organic molecules. Like water, it is a polar solvent capable of pulling atoms together and enabling them to interact. It has rules of its own, rhythms of its own, and a quiet potential for complexity. When we imagine life, we often picture Earth's familiar beauty: rolling forests, deep oceans, meadows shimmering in sunlight. But there are far richer palettes in the universe, colors we have not yet learned to expect. Worlds covered in liquid ammonia might glow gold or copper beneath dim starlight. Their skies could be tinted orange or red, painted by gases unfamiliar to us. Light would behave differently there. Shadows might fall in shades we cannot name. Forms of life, if they existed, would not resemble anything from Earth. Their metabolisms would be shaped by cold, their movements slowed by low temperatures, their cellular chemistry sculpted by the properties of ammonia. This humble molecule, one nitrogen atom bound to 3 hydrogen atoms, may hold the key to a type of life far from Earth's geocentric definitions. Ammonia is surprising because it behaves enough like water to support chemical reactions, but operates under an entirely different range of temperatures. It has a lower boiling point and freezing point, meaning it remains fluid when earthly organisms would freeze solid. On a planet where the average temperature lingers far below what humans could survive, life might still flourish in oceans of ammonia. Imagine such a world, a landscape where the ground crackles with frost, where every exhale would crystallize in the air, where sunlight is pale and distant, and beneath that frozen crust, seas of liquid ammonia stretch outward, rippling softly with every whisper of wind. Organisms, if they exist there, would be born from these golden waters. Their structures would reflect the colder chemistry, their colors different, their senses shaped by the faint light of their star. Forests, if they existed at all, would not be green. Rivers would not sparkle blue. Life would carry an elegance foreign to our eyes. Just as Earth has its water cycle: evaporation, condensation, rain, an ammonia world would have its own cycle, shaped by temperatures too cold for human habitation. Ammonia would rise from golden seas, gather into clouds of amber and pale orange, drift through icy winds, then fall again as ammonia rain, tracing patterns across metallic landscapes. It would carve valleys through nitrogen-rich soil, floodplains briefly, then retreat in slow tides. Entire ecosystems could live in harmony with this cycle, breathing, dividing, flourishing in a world where cold is not a boundary, but a foundation. Life, it seems, could take shapes that sidestep every expectation we hold. It could hide in places we once believed barren. It could bloom under rules we have yet to imagine. It could thrive in solvents other than water, in temperatures considered impossible, under skies heavy with gases Earth organisms could never breathe. The cosmos reminds us again and again that our understanding is only a beginning, and that the universe is too vast for certainty. Somewhere out there, ammonia might fall as rain upon a world where life wakes slowly under a distant sun, completing its silent cycle in rhythms we have not yet learned to hear, complete with ammonia, clouds, ammonia rain. Perhaps, in those distant worlds we pictured before, the cycle of ammonia would not stop at clouds and rain. It might even bring with it something like snow, slow drifting crystals of frozen ammonia, falling out of a darkened sky onto plains that never know the softness of liquid water. Each flake would be a tiny sculpture of cold chemistry, settling on the surface, melting back into liquid during brief, gentle thaws, then rising once again as vapor. This constant motion, this quiet circulation between sky and ground, would be essential for any life that called such a world home. It would keep the environment from becoming still and unchanging. It would move nutrients, rearrange molecules, and carve out pockets where something living could take shelter from the harshness above. If life can endure the extremes of Earth, it becomes easier to imagine its persistence elsewhere, on our own planet. Organisms have been found in acidic lakes, where the water would burn human skin, clinging to rocks beside deep-sea hydrothermal vents, where temperatures and pressures crush almost all other forms of life. Microbes survive in frozen deserts, in thick salt brines, even inside rocks themselves. These creatures remind us that life does not always choose comfort. It presses into unpredictable corners, reshaping itself to survive in environments we once believed utterly hostile. When we remember this, the idea of an ammonia-rich exoplanet with cold seas and alien skies no longer feels impossible. It feels like one more canvas for biology to explore. This possibility carries enough weight to rewrite textbooks and stretch the boundaries of what we call life. To understand it, though, we must look closely at two central players in our own biology: carbon and water. Both are indispensable here, yet their roles differ in important ways. Carbon builds, water connects. Carbon is the skeleton of life's molecules, while water is the space in which those molecules meet. When we talk about alternative biochemistry, it helps to separate these functions in our minds so we can imagine what happens if one is replaced and the other is not. Carbon is the base of every known life form on Earth. It is a nimble element, able to form large, stable structures like proteins, lipids, and the strands of deoxyribonucleic acid that carry our genetic instructions. Its ability to form 4 bonds at once allows it to act as a central hub, linking many atoms together into shapes that twist, fold, and respond. From enzymes that speed up reactions to membranes that enclose cells, carbon sits at the heart of nearly everything. It is the storyteller of our chemistry, shaping the characters and patterns that allow us to grow, heal, and think. Water, by contrast, is the stage where the story unfolds. It is a solvent, a fluid medium that allows molecules to move, collide, and interact. In water, ions drift, proteins fold, sugars dissolve, and membranes form. Reactions that would be rare in dry conditions become frequent and reliable in liquid water. In that sense, if carbon is the actor, water is the theater. It is the space, the lighting, the air, the backdrop. Without it, the drama of life, at least as we know it, could not proceed in the same way. If we try to replace carbon, we quickly run into near impossible challenges. Few elements can form the same variety of stable, flexible structures. Silicon comes closest on paper, but falters in practice. Reimagining life's building blocks without carbon would mean rebuilding the entire script of biology from the ground up. It is a feat that our chemistry has not yet shown any candidate element ready to perform. Replacing water, however, leads us into a slightly different conversation. There, the question is not whether any chemical frameworks can exist without water, but whether another solvent could play a similar supporting role. Ammonia steps quietly into that discussion. Like water, it is a polar solvent, meaning it carries partial electrical charges that help it dissolve other substances. It can act as a medium, where molecules meet and react. The main difference lies in the temperature range, where ammonia is liquid. Rather than flowing under the mild warmth Earth enjoys, ammonia remains liquid in much colder climates. This means that any biology relying on ammonia instead of water would operate in a slower, more subdued world. Chemical reactions would proceed at a gentler pace. Life, if it arose there, might move and change more slowly than we do, its metabolism tuned to the quiet rhythm of the cold. In an ammonia-based world, cells would need to adapt completely to their unusual surroundings. Their membranes might be made from lipids that remain flexible in ammonia, rather than those that work in water. Enzymes, the biological catalysts that speed up life's processes, would need to be shaped to function at low temperatures and in a different solvent. The genetic material carrying their instructions might still resemble deoxyribonucleic acid or ribonucleic acid in principle, but its base pairs and structure could be altered to suit an ammonia-rich environment. Some scientists gently suggest that such molecules might favor different chemical groups, better suited to stability in that cold, unconventional sea. When we consider life beyond Earth, the question is not only where to look, but what to look for. If we expect only carbon-based life swimming in water, we will design instruments that search exclusively for those signs. But if we allow ourselves to consider ammonia-based life, we must expand our imagination. We must picture different kinds of cells, different reaction rates, different pigments, and different waste products. We must ask new questions of the light we observe, the spectra we measure, and the atmospheres we analyze. Examining the biochemistry of an ammonia-based organism is like sketching a picture in dim light. We do not see clearly, but we can outline possibilities. In such a creature, ammonia would take the place of water as the solvent that carries molecules. The reactions inside its cells would be catalyzed by enzymes tuned to this chill, reactive environment. These enzymes might be built from amino acids modified to be stable at low temperatures and within ammonia's chemical rules. Their shapes would still curve and fold, but perhaps less dynamically, conserving movement and energy. Because cold slows everything down, metabolism in these organisms would likely be slower than in ours. Growth, repair, and reproduction might take years, where ours take days. Even communication between cells could proceed at a more deliberate pace. Yet slowness does not mean lifelessness. It simply means a different measure of time. From the perspective of such organisms, their lives would feel as full and active as ours do, only stretched across longer intervals. What might these beings look like? It is difficult to say with any confidence, but we can imagine forms suited to their world. In environments with lower gravity and colder temperatures, skeletons might be flexible and elastic, bending gently rather than resisting with rigid strength. Bodies could be soft and layered, insulating delicate chemistry from the bitter chill outside. Plants, if such organisms exist, might use pigments tuned to their star's light. If their sun shines more strongly in blue or violet wavelengths, their equivalent of chlorophyll could be darker, absorbing those colors more efficiently. Fields of such plants might glow deep indigo or violet under a dim sky. The surfaces of these distant planets could be dotted with shimmering growths, tendrils of life unfurling slowly over ages. Creatures might glide through ammonia seas, buoyed by the thick, cold liquid, their movements deliberate and calm. Their senses could be based on pressure, temperature, or faint chemical gradients rather than sound and color. To us, they might appear almost motionless. To them, their world would be filled with constant change. These ideas are not only gentle speculation, they hold real consequences for how we design our future missions. If we want to find life that does not resemble Earth, we must build tools that can see beyond Earth-like patterns. Instruments that detect only water and oxygen might miss signs of ammonia and other alternative solvents. Spectrometers could be tuned to notice unusual combinations of gases that might indicate ammonia-based biology, imbalances in nitrogen compounds, unexpected levels of certain organic molecules, or patterns of absorption that hint at exotic pigments. Future probes sent to the icy moons of Jupiter and Saturn, or to distant dwarf planets, might need drills and sensors capable of sampling both water ice and possible pockets of ammonia. Orbiters watching exoplanets as they pass in front of their stars could be equipped to look for subtle hints of ammonia in their atmospheres, measuring not only the presence of certain gases, but how those gases shift over time. Changes in ammonia levels might betray seasonal cycles, weather patterns, or perhaps even the slow breathing of a biosphere. Rethinking our search in this way expands the playing field dramatically. Until now, our efforts have been shaped largely by a geocentric perspective. We have pointed telescopes and sent probes toward places that look most like home, following the comforting logic that life will repeat itself. If we widen that view to include ammonia-based possibilities, the number of potential habitats grows enormously. Worlds once considered too cold or too strange begin to seem worth a second glance. This shift would affect mission planning at its core. Objectives would need to include the detection of non-aqueous solvents. Instruments would be calibrated not just to sniff out water vapor or oxygen, but also to sense ammonia and related compounds. Data analysis teams would be trained to recognize spectral signatures that hint at unfamiliar chemistries. Even the questions that guide our proposals would change from, "Is there another Earth?" to, "What else can life make possible?" The discovery of even a microscopic form of ammonia-based life would reshape more than science. It would ripple into philosophy, ethics, and our own sense of identity. Knowing that life can arise from such different conditions would force us to reconsider how special or how common we truly are. Are we a rare exception, or merely one example of a universal tendency for matter to organize itself into something that feels and wonders? Ethical questions would follow. If we encountered such life, even in the form of simple microbes, how should we treat it? Would we have the right to sample, alter, or interfere with its environment? Would we view it as fragile and sacred, or as data to be collected? Our choices would say much about how we see ourselves in relation to the universe. Our art, literature, and quiet late-night conversations would change too. People might look up at the night sky with a different gentleness, knowing that some of those faint, cold points of light could host not only oceans and rock, but entirely new stories of chemistry slowly learning to feel. Religions and philosophies might revisit old questions about what it means to be alive, and whether awareness has many possible homes. Even the simple act of filling a glass with water could feel slightly different, colored by the knowledge that somewhere far away, another kind of life might be lifting a cup of something colder, stranger, yet just as vital. Education would transform as well. Textbooks in biology might grow new chapters devoted to alternative biochemistry, exploring not just water and carbon, but ammonia and other solvents. Students would learn from an early age that life is not necessarily confined to one set of rules. Astrobiology, once a niche field, could become a standard part of science curricula, inspiring children to imagine worlds very different from our own, and to ask questions we have not yet thought to pose. In quiet classrooms lit by afternoon sun, They might read about ammonia oceans and flexible skeletons, about far-off clouds and slow, patient metabolisms, and feel a stirring of curiosity that will guide them for years to come, gently inspiring a new generation of scientists. To think beyond Earth's limits is to let the mind step gently past the edges of what feels familiar. When we dare to imagine that life might blossom in seas of ammonia, beneath skies tinted copper and gold, we are really doing something quiet and profound. We are admitting that the universe may be far more inventive than our habits of thought. Standing on the threshold of this wider frontier, the realization that ammonia could be a genuine cornerstone of life does more than tweak a page in a textbook. It stretches our horizons, invites us to question long-held assumptions, and opens a universe of possibilities that may begin with a simple molecule, but do not end there. From that single, sharp-scented compound, whole worlds could unfold, worlds whose stories we have not yet learned to read. When we loosen our grip on what we consider normal, something else happens too. Our thoughts begin to drift toward other foundations we rarely question, other invisible frameworks that quietly shape our days. One of the deepest of these is time itself. We plan our lives around it, measure our years with it, feel it pressing or slipping, heavy or light. Yet when we look closely, this most fundamental texture of our experience starts to shimmer with uncertainty. What if one of the pillars we lean on the most is, at least in part, a carefully woven illusion? Time seems to be everywhere at once. It ticks in the quiet corner of a bedroom at night. It scrolls across digital screens and hides in the beating of a heart. It appears to govern our routines, to dictate the rhythm of our lives. But physics suggests that time is not as simple or as steady as it appears. For objects moving close to the speed of light, time slows down. In regions where gravity is strong, time itself stretches and drags, flowing differently than it does in calmer places. These effects have been measured and confirmed, not just imagined. They hint at a strange truth. The ticking we trust may not be the same for everyone, everywhere. Have you ever noticed how time seems to change its pace depending on what you are feeling? Moments of joy vanish too quickly, while minutes of fear or sadness seem to drag on without end. Childhood summers feel impossibly long in memory, while adult years slip by with unnerving speed. Our brains do not measure time like clocks. They stitch it together from experiences, from emotion, from attention. Different cultures even teach different ways of relating to time, some as a rigid sequence, some as a fluid cycle. All of this suggests that time, as we live it, is not a single universal stream. It is a flexible impression shaped by our minds. In its simplest form, time is a tool we created to keep track of change. Long before there were watches or calendars, there were needs. Our ancestors had to know when to plant seeds and when to harvest, when floods would come and when herds would migrate. They watched the sky as their first clock. The rising and setting of the sun offered a reliable heartbeat. The phases of the moon traced out a gentle monthly rhythm. The slow drift of familiar stars across the night sky marked the passage of seasons. These natural cycles were the first lines on the invisible ruler we now call time. As human societies grew more complex, so did their methods of timekeeping. Sundials carved shadows into meaning, turning the path of the sun into hours. Water clocks let drops fall in steady intervals, quietly measuring the passing moments in temples and palaces. Later, mechanical clocks appeared, full of gears and springs, with hands circling faces marked with numbers. They sliced the day into smaller, more precise pieces, making it easier to coordinate work, trade, travel, and ritual. Calendars arose alongside them, organizing days into months and years. Different cultures stitched time into different patterns: lunar calendars, solar calendars, and mixtures of both, each reflecting its people's way of understanding the world. Yet even as our tools for measuring time grew more accurate, the feeling of time remained elusive and deeply personal. A single afternoon can feel long to one person and fleeting to another, even if the same number of minutes has slipped past. Age plays a role. A year is a huge fraction of a child's life, but a smaller slice of an adult's memory. Emotion plays a role too. Waiting in a hospital corridor stretches time out like a thin, uneasy thread, while an evening spent with someone you love seems to fold in on itself, over almost before it has begun. In this way, time is not only a physical quantity, it is also a story the brain tells about change. This raises an unsettling question. Is time an objective feature of the universe, or is it primarily a construct we have built to make sense of motion, change, and memory? The answer, as far as we can tell, lies somewhere in between. There is something real that our clocks and calendars are trying to describe, but our perception of it is filtered through nerves and neurons, expectations and culture. To get closer to the underlying reality, we have to step out of our everyday intuitions and follow a different kind of guide: physics. For centuries, time in physics was treated as a universal, steady backdrop. It flowed, in theory, at the same rate everywhere, unaffected by anything that happened within it. This view was comfortable and simple. Then, in the early 20th century, a quiet revolution began. A young physicist, Albert Einstein, questioned assumptions that had stood unchallenged for generations. Working with thought experiments rather than grand laboratories, he probed the nature of light and challenged the idea of absolute space and absolute time. Einstein proposed that the fundamental laws of physics should look the same to all observers, no matter how they happen to be moving, as long as their motion is steady and not accelerating. From this gentle but radical idea emerged the special theory of relativity. One of its most surprising consequences is that space and time cannot be separated cleanly. They are intertwined into a single fabric called space-time. Instead of thinking of 3 dimensions of space and a separate ticking of time, Einstein invited us to picture a 4-dimensional structure where every event, a star's flare, a falling leaf, a whispered word, is a point in space-time. In this view, time becomes the 4th dimension, inseparable from the 3 dimensions of space. When you move through space, you are also moving through time, and how you move affects how you experience both. This concept shattered the traditional idea of time as a universal and independent river flowing the same way for everyone. It revealed that what one observer calls now may not match another's now if the two are moving relative to each other. The idea that events simply happen in a single shared order for all observers turns out to be an illusion born of our slow speeds and limited perspective. One of the key insights of special relativity is that simultaneity, the idea that 2 events happen at the same time, is not absolute. Imagine 2 lightning strikes hitting opposite ends of a long train track. To a person standing on the ground midway between the strikes, they may appear to happen at exactly the same moment. But for someone riding on a train, rushing along the track, moving closer to one strike and away from the other, the flashes will not seem simultaneous. What counts as at the same time depends on how you are moving. Time, in other words, is woven into motion. Another startling result is time dilation. When two observers move relative to one another at high speed, each experiences their own proper time, the ticking of their own clocks, and the beating of their own hearts, as normal. Yet, when they compare notes later, they will find that time has flowed differently for each of them. The faster an object travels through space, the slower time passes for it compared to someone who remains at rest. This is not a trick of perception or a flaw in the clock. It is a real feature of space-time itself, confirmed by experiments with fast-moving particles and high-speed aircraft carrying precise timepieces. Einstein did not stop there. He extended these ideas into a broader framework called the general theory of relativity, which brought gravity into the picture. In this theory, gravity is no longer a mysterious force pulling objects together from a distance. Instead, massive objects like planets, stars, and galaxies bend the space-time around them. Smaller objects follow the curves and dips created by this bending, and we experience their motion as the pull of gravity. A planet or star can be imagined as resting on a flexible sheet, warping it. Marbles placed on the sheet roll along the curves created by the heavy weight. This warping of space-time does more than guide motion. It also affects the flow of time. Near a massive object, where space-time is more strongly curved, time runs more slowly compared to regions farther away. This effect is called gravitational time dilation. Two clocks ticking at different gravitational strengths will not agree when brought together. The one that spent time deeper in the gravitational well, closer to the massive body, will have recorded less time passing. This is not speculation. Sensitive clocks on satellites and on the surface of Earth show measurable differences. Engineers must account for these relativistic effects for systems like global positioning satellites to work correctly. Combined, special and general relativity paint a picture of time that is deeply different from our common sense. Time does not simply march forward at a steady pace, identical everywhere. It stretches and compresses depending on speed and gravity. An astronaut traveling at a significant fraction of the speed of light, or resting near a dense, massive object, would genuinely age more slowly relative to someone who stayed at home in a gentler gravitational field and at slower speeds. Both would feel their own time as normal, yet their experiences would diverge. The famous twin paradox is a gentle way to visualize this. Imagine a pair of twins who begin their lives together on Earth. One twin remains at home, living an ordinary life under the familiar pull of Earth's gravity. The other climbs aboard a spacecraft capable of reaching speeds close to the speed of light. For the traveling twin, days and nights aboard the ship flow in what feels like a normal rhythm. They read, dream, think, and watch stars slide slowly by the window. Time, for them, feels ordinary. Meanwhile, back on Earth, the stay-at-home twin continues to age, measuring years with changing seasons, birthdays, and quiet evenings. From their perspective, the traveler has gone away for a long and daring journey. When the traveling twin finally turns the ship around and returns home, both twins stand side by side once more and compare their ages. To their shared astonishment, the twin who flew among the stars is physically younger than the twin who remained on Earth. More time has passed for the one who stayed still than for the one who sped through space. The difference is not metaphorical, it is written into their bodies. This strange outcome is a direct result of time dilation. Moving close to the speed of light causes time to slow for the traveler relative to the one at rest. Their path through space-time, bent by high velocity and changes in motion, leads them to a different total amount of experienced time. In this quiet, almost melancholy way, relativity whispers that time is not a single shared current in which we all drift together. Instead, each of us moves along our own thread of spacetime, and those threads can stretch at slightly different rates depending on where we go and how we move. Upon return, the traveling twin will indeed be younger than the Earth twin because of this very real, very gentle warping of time. In general relativity, the slowing of time is not only tied to motion, it is also woven into the quiet pull of gravity. Wherever gravity is stronger, time flows more slowly. Wherever gravity relaxes its grip, time runs a little faster. Close to massive celestial bodies, such as planets, stars, or dense remnants like neutron stars, the fabric of space-time is bowed more deeply, and the river of time pools and thickens. Farther away, where the gravitational field grows weaker, that same river seems to run more freely. We do not feel this difference in our everyday lives, yet it is there, subtle and persistent, shaping the way moments add up. One of the most delicate ways we have tested this effect is with atomic clocks, instruments so precise they can lose or gain less than a whisper of a second over millions of years. When scientists place one atomic clock high on a mountain and leave another at sea level, they are, in a sense, perching two tiny guardians of time at different depths in Earth's gravitational well. The clock closer to Earth's center, where gravity is slightly stronger, ticks more slowly than the one higher up. After some time has passed and the clocks are brought back together and compared, they no longer agree perfectly. The difference is tiny, but it is real, and it matches the predictions of general relativity. This slowing of time under gravity may sound almost mythical, as if we were telling a story about enchanted valleys and swift hilltops. Yet, it has been measured again and again, and it quietly supports technologies we rely on every day. One of the clearest examples is the Global Positioning System, the network of satellites circling far above Earth that helps us find our way. Each of these satellites carries its own atomic clock, ticking away in the thin upper layers of Earth's gravitational field, moving at high speed relative to the surface below. Because of this, time aboard the satellites passes at a slightly different rate than it does on the ground. If engineers ignored relativity and treated time as perfectly uniform everywhere, the positions calculated by global positioning devices would drift. At first, the errors would be small, barely noticeable, on a short walk through a city. But with each hour, each day, they would grow. Within a short span of time, locations would be off by hundreds or even thousands of meters. Maps would become unreliable, navigation would falter, and the quiet trust we place in that glowing blue dot showing our position would be broken. Instead, the equations running underneath these systems gently correct for both the speed of the satellites and the strength of gravity at their altitude. Relativity is not an abstract idea locked in textbooks. It is built into the devices we carry. Time dilation has also been confirmed in the hidden corridors of particle accelerators, where subatomic particles race around long circular tracks at speeds approaching that of light. Many of these particles are unstable. At rest, they decay in a fraction of a second, winking out of existence almost as soon as they appear. But when they are launched to near light speeds, they survive longer than they should, as if someone had quietly stretched out their lifetimes. The faster they move, the more pronounced this effect becomes. Experiments measuring their decay rates match the predictions of special relativity with remarkable precision. It is another soft but undeniable reminder that high speeds and strong gravity truly do bend time. Before Einstein, Most physicists followed a view of time shaped largely by the work of Sir Isaac Newton. In Newton's picture, time was absolute, an invisible, universal backdrop that flowed at the same rate everywhere, independent of everything that happened within it. Events took place against this steady background, the way actors move across a fixed stage. Whether planets drifted in their orbits or stones fell to the ground, time itself remained unchanged, impartial, and indifferent. The discoveries of relativity altered this serene image, with the realization that time can stretch and compress depending on motion and gravity. The idea of a single universal clock ticking the same way for all observers had to be abandoned. Time, it turned out, was not a rigid frame, but a responsive part of the universe, entangled with space itself. This does not mean that anything can happen in any order, but it does mean that our old certainty about how events are arranged begins to loosen and soften around the edges. The traditional view of time also carries a strong sense of causality. Cause must always precede effect. A stone must be thrown before a window breaks. A match must be struck before a fire begins. In everyday life, this order feels unquestionable. Yet in relativity, the sequence of events can depend on who is watching and how they are moving. Two events that seem to occur in one order for a stationary observer might appear reversed or nearly simultaneous for someone rushing past at high speed. In most cases, the universe protects causality so that information cannot travel faster than light, preserving a deeper order beneath the shifting appearances. Still, the very fact that the when of events can change from one observer to another challenges our intuition about how strictly the story of the universe must be read. This leads us to an idea known as the arrow of time, the sense that time has a single direction, always flowing from past to future, never backward. We feel it in the way memories accumulate behind us, while possibilities stretch ahead. We see it in the way a cup, once shattered, does not leap back together, and in the way we grow older but never younger. The arrow of time feels absolute. Yet relativity, with its flexible ordering of events, invites us to ask whether this arrow is truly fundamental, or whether it might emerge from how we, as observers, made of matter and memory, perceive the unfolding of change. As the picture of time as an absolute background has softened, some scientists and philosophers have begun to wonder if time itself might be an emergent property rather than a basic ingredient of reality. In this view, time arises from the relations and interactions between things, rather than existing as something separate that they move through. Just as a city's hum is not a single sound, but the blending of countless footsteps, voices, engines, and birdsong, the flow of time might be a pattern that emerges from innumerable processes layered on top of one another. From this perspective, asking where time really is might be like asking where a melody lives when no one is singing. If relativity gently bends our understanding of time on large scales and high speeds, quantum mechanics unsettles it at the smallest scales imaginable. Venturing into the quantum realm is like stepping into a room where familiar rules have been rearranged. Here, particles do not behave like tiny billiard balls following precise paths. Instead, they act more like ripples of possibilities spread out through space. Quantum mechanics studies the behavior of particles at atomic and subatomic levels, and it is governed by rules of probability rather than certainty. In the quantum world, a particle can exist in several possible states at once. It can be here and there, spinning this way and that, all at the same time. In a delicate condition called superposition, Only when we interact with the particle in a specific way, when we measure its position or its momentum or some other property, does it choose one definite outcome. Before that moment of measurement, its state is best described as a cloud of possibilities rather than a single, sharp fact. Time in quantum mechanics plays a different role than it does in classical physics. In the old equations of motion, time is continuous and absolute, a smooth parameter that marches forward without interruption. In many formulations of quantum theory, time enters the mathematics as a parameter against which the evolving probabilities are described, rather than as a tangible substance. This can make it feel as though time has become more abstract, less like a flowing river, and more like a bookkeeping symbol that helps us track changes in the wave-like states of particles. In some approaches, time may even appear in tiny discrete steps, or lose its conventional meaning altogether when we move toward the realm where quantum effects of gravity become important. To glimpse how observation changes things in the quantum world, consider an everyday scene. Imagine sitting very still at the edge of a forest clearing, watching a group of animals foraging. When they do not know you are there, their movements are relaxed and natural. But as soon as they sense your presence, if a twig snaps under your foot or a shadow shifts, they start behaving differently. They might flee, freeze, or circle warily. Your attempt to observe them has altered what you are trying to study. In quantum mechanics, this observer effect becomes even more striking. When we measure a quantum object, such as an electron, we cannot simply peek without touching. Any attempt to find out where it is or how fast it is moving involves interacting with it, perhaps by scattering light off it or by using another particle as a probe. This interaction inevitably disturbs the object's state. Properties like position and momentum become fuzzy under such scrutiny, not because our instruments are clumsy, but because the quantum world itself does not allow both to be sharp at once. This limitation is captured by Heisenberg's uncertainty principle. It tells us that the more precisely we pin down a particle's position, the less precisely we can know its momentum, and vice versa. There is a built-in trade-off, rooted in the nature of reality, not just in our skill at measurement. It is as if the universe has drawn a soft line, saying that certain pairs of questions cannot both be answered with perfect clarity at the same time. When we do perform a measurement, something dramatic happens at the level of description. The particle's wave function, a mathematical object that encodes all its possible states, collapses from a spread-out haze of probabilities into one definite outcome. A particle that could have been in many places is found in just one. A spin that could have pointed in several directions is revealed to point in a single one. This collapse is not like a classical object changing its mind. Rather, it is the moment when the world chooses, from among allowed possibilities, one reality to present to our instruments. Because this process is inherently probabilistic, the exact outcome of any single measurement cannot be predicted with certainty. We can know the odds, but not the specific result. Over many repetitions, patterns emerge that match quantum predictions. But each individual event unfolds like a tiny coin toss that obeys deeper rules we cannot see directly. Taking together the phenomena of quantum superposition and the observer effect, a different picture of time begins to shimmer at the edges of our understanding. On the quantum level, the neat, linear progression from past to present to future seems to blur. States exist as mixtures of could be, not yet committed to is or was. The act of observation does more than reveal what was already there. It helps define what becomes real. Time, in this view, looks less like a straight arrow and more like a tapestry woven from countless probabilistic threads. each measurement tying one of them down. Seen from this vantage point, our traditional idea of time as a simple, unbroken line may be too narrow. At cosmic scales, relativity tells us that time bends and stretches with motion and gravity. At quantum scales, time seems to lose some of its familiar solidity, entangled with knowledge, probability, and the act of observation itself. In the gentle tension between these two realms, our understanding of time is still very much a work in progress. Time is closely intertwined with our understanding of space, and in the last century, that bond has become harder and harder to ignore. The more we learn about how light moves, how gravity bends, how particles behave, the more it seems that time and space are not two separate stages on which the universe plays out its scenes, but parts of a single woven fabric. From this fabric, many different theories have been pulled, each trying to explain what space-time really is and what it means for us. Among them, one idea stands out as especially haunting and thought-provoking: the block universe. The block universe view, sometimes called eternalism, or the space-time block perspective, grows naturally out of Einstein's relativity. It takes seriously the notion that space and time form a single four-dimensional structure, and then asks, very calmly, what that actually implies. According to this picture, the past, the present, and the future are not separate realms strung out like beads on a cord. Instead, they are all parts of one immense, four-dimensional whole called space-time. In that whole, every event, from the first flickers after the birth of the universe to scenes unimaginably far in the future, coexists in a single vast block. To imagine this, it can help to step away from clocks entirely and think of a simple object you can hold in your hands. Picture a clear crystal paperweight with tiny shapes frozen inside at different depths. From one angle, you might see only the figures near the front. From another, deeper shapes appear. Nothing inside the crystal is moving from front to back. All the patterns are already there. What changes is only the way you look through it. The block universe suggests that reality might be like that crystal. All of space-time, every moment, every place is present in the block. What we call now is just the thin slice of that structure our consciousness happens to be aligned with. In relativity, each event is a point in space-time, marked not only by where it is, but also by when it is. Your birth, your first day of school, this moment as you listen, and some quiet future evening you have not yet lived. All of them correspond to different points along a single path through space-time. That path, your world line, is like a trail traced in the four-dimensional block. The past is not gone. The future is not yet. Instead, in this view, both are simply different regions along the trail. Our sense that the past has vanished and the future is empty may be less a statement about reality and more a reflection of how our minds move. The block universe picture tells us that time does not flow the way a river does. Rather, it is one dimension within space-time, laid out from beginning to end. The flow we feel may be a kind of mental motion, awareness sliding along the world line, touching one event after another. You can think of it the way you think of reading a book. All the words, sentences, and chapters of the story exist at once on the printed pages. The ending is already written, whether you have read it or not. Yet your experience as a reader is linear. You turn pages one by one. You meet characters, watch them change, feel suspense about what comes next, even though the outcome is already waiting further ahead. In much the same way, says the block universe view, Our lives unfold not because the future is being created in real time, but because our conscious attention is moving through a story that, in some sense, already has a full shape in space-time. This way of seeing things can be unsettling, even when it is described in a whisper. If all events from ancient supernovas to tomorrow's small choices coexist in the space-time block, then what does that say about free will? Are our decisions just lines already etched into the structure of the cosmos? Is the feeling of, "I could have done otherwise," merely a kind of illusion that arises because we have not yet reached the part of our world line where the consequence appears? Philosophers and physicists have argued about this for decades, and perhaps the debate will never fully settle. Some people believe that free will and the block universe are compatible. In their view, your choices are still truly yours. They arise from your character, your thoughts, your emotions, and the particular circumstances you inhabit. Those internal processes are as much a part of space-time as anything else. The fact that they are already there in the block does not make them less real. It simply means that the universe, taken as a whole, contains the entire history of those choices all at once. Others lean toward a more austere reading. If the block universe is correct, they say, then the cosmos might be fundamentally deterministic, at least at the macroscopic level. Our actions would then be the unfolding of physical laws written into the structure of space-time, and our feeling of steering ourselves might be like the way a character in a story experiences choice, even though the author has already decided how the plot will end. In that picture, free will becomes less like a power and more like a deeply convincing part of the story we tell ourselves from the inside. Whichever side you find more persuasive, the block universe gently pushes us to rethink what we mean when we speak about the future. In everyday language, the future sounds like a region that does not yet exist, a blank space waiting to be filled. In the block view, however, the future is more like an unread chapter. It is not open in front of us, but it might already exist within the book of space-time. We are not so much building the future from nothing as walking into parts of the block we have not yet visited. This theory does not only touch free will and personal identity, it also raises deep questions about reality itself. If all events coexist in space-time, is the universe static in some ultimate sense, with nothing ever truly becoming or ceasing, only being in different regions of the block? Or is the flow of time, the felt passage from moment to moment, an essential ingredient of reality, something that cannot be peeled away as mere illusion? Perhaps the structure of space-time is the canvas, and our conscious experience of time is the moving light that brings certain parts of the painting into view. These are not questions with easy answers. The block universe is, at its core, a way of taking relativity seriously and following its implications wherever they lead, even into uncomfortable territory. Yet whether or not the block picture is literally true, exploring it helps us see our ordinary intuitions in a new light. It prompts us to ask what it really means to say that something happened, or will happen, or is happening right now, when different observers in different states of motion can disagree about which events belong to which category. In daily life, time feels simpler than this. We lean on the passage of hours and days to structure our routines. We wake, work, rest, and dream according to schedules. We remember things that have occurred and cannot be altered. We anticipate things that have not yet taken place and may still change. Time lets us perceive growth and decline, to trace stories from beginning to middle to end. It allows us to take experiences that would otherwise be a chaotic jumble and arrange them into a narrative. This came first, then that followed, and because of this, that occurred. In this way, time is not only a physical parameter, it is also the backbone of our personal sense of meaning. Yet the more carefully we look, the more paradoxical time becomes. Physics tells us that there is no single universal now valid for everyone. Relativity shows that the order of events can depend on the observer's frame of reference. Quantum theory suggests that what is real may not be fully settled until interactions occur, and that some of what we call evolution in time might be tied to how information is exchanged. Philosophical views, like the block universe, argue that past, present, and future might all be equally real in a way our senses cannot easily grasp. Meanwhile, our brains continue to experience time as a river that always moves in one direction, from what was to what is to what will be. It is as if we inhabit two worlds at once. In one, time is the familiar medium through which we live and feel. In the other, time is a more elusive quantity, shaped by motion, gravity, probability, and perspective, not easily pinned down or even guaranteed to exist as we imagine it. Instead of being discouraged by this tension, we can let it soften us. It reminds us that our everyday view, while useful and precious, is not the only way reality can appear. In our ordinary hours, time helps us plan, hope, remember, and heal. In our scientific investigations, it becomes a doorway into some of the strangest features of the universe. The paradox at its heart, that time is both central to our lives and possibly not as fundamental as we think, makes it one of the most intriguing mysteries we have. Whether time is a basic thread in the fabric of the cosmos or an emergent pattern arising from deeper relations, it continues to guide everything we experience. When we lie awake at night, thinking back over the day, we often replay small scenes: a conversation by a window, a message we received, a walk we took as the light was fading. We rarely pause to notice that, in the larger picture of space-time, those scenes do not simply evaporate the way they seem to in our feelings. They settle into the block of the universe like faint points of light fixed in their coordinates while we move on. Our memories are like lanterns shining backward along our world lines, lighting a few stretches of that block and leaving the rest in darkness. The same is true when we imagine the future. Inside our minds, we sketch moments that have not yet arrived, rooms we have not entered, faces we have not met. From where we stand, they are still only possibilities, hopes, or quiet worries. Yet in the block universe picture, there is at least the suggestion that such moments may already have their places in space-time, waiting somewhere ahead along our world lines. Whether time is ultimately a fixed block or something more fluid and unfinished, what remains within our reach is the choice to stay curious, to keep questioning, keep listening, and keep gently opening ourselves to new ways of seeing the universe and the quiet, mysterious thing we have learned to call time.